Previously we learned about wave particle duality and also about the photoelectric effect. That was in chapter 5.4, part 1 and part 2 respectively. Now we will go to part 3 where we have electron diffraction and interference. Remember, we learned that electron is a particle and also it has some wave properties. That's why we learned about the wave particle duality. So if it is having properties of waves, that means it can be diffracted, and also you have learned that waves undergo interference. Waves can be reflected, refracted, diffracted, and also remember they can interfere. Once they are diffracted, they can interfere. So we will see how it applies to electrons here, because electrons have properties of waves. By the end of this section, you should be able to explain how diffraction experiments provide evidence for the wave nature of electrons. So this is what you will learn. Describe other evidence for the wave nature of electrons. Wave nature of electrons, describe other evidence. So we will see, be able to use the de Broglie equation. This is pronounced Broglie even though it's spelled with a letter G. De Broglie equation, lambda equals h over p. This lambda is called the de Broglie wavelength. H is the Planck's constant. You have seen it previously when you learned about the photoelectric equation. Remember, E equals hf, energy of photon, is the Planck's constant times the frequency. Then P is the momentum. Momentum is mass times velocity. We have seen that waves passing through a gap will produce a diffraction pattern with bright and dark fringes as the diffracted waves from each side of the gap superpose to produce the interference pattern. This was learnt in a previous chapter when you learnt about waves. Now you learnt about the Young's double slit experiment, where light was a monochromatic light was passed through a slit, and after that there was a double slit. First it passed through single slit, it got diffracted, then it was passed through double slit, or you can directly do it with the double slit also. Then you have diffraction on the other side, and since the diffraction occurs at two slits, at each slit, on the other side those waves interfere. When they interfere, they produce the pattern. We have seen that waves passing through a gap will produce a diffraction pattern with bright and dark fringes as the diffracted waves from each side of the gap superpose to produce the interference pattern. Now this is in the case of waves. Now we will see how this applies to electron diffraction. Now this is what you have seen, circular diffraction pattern caused by a laser passing through a pinhole. So this is just a single slit or a pinhole. So if you have two of these, diffracts, and after that you have interference which produces the bright and dark fringes. Okay, so we will see now about electron diffraction. As a diffraction pattern is a wave phenomenon, to observe this from a beam of electrons means they must be behaving as waves. So this is what I mentioned earlier. This is true when we are passing waves through a gap, as in figure A. In this case you can see here the diffraction pattern for this monochromatic light from the laser. Mono means one color, so you can see just the red color. This is true whether we are passing waves through a gap, as in figure A, or reflecting waves from a grating, as we saw in figure H of section 5.2.3. Now we are in 5.4.3. So if you go back to 5.2.3, you can see it. Let's quickly go up. Alright, so you can see 5.2.3. This is diffraction of waves. See, this is the single slit or aperture, also called hole. Then you have diffraction like this. Now when the size of the gap is equal to the size of the wavelength of the waves, then prominent or noticeable diffraction occurs, because it is the same size, like you see here. If it is too big, then less diffraction. So even diffraction can occur around a edge also. and this is the pattern that we were talking about. So with the single slit you have that. Remember in the chapter we are discussing also the diagram was there, but if you send it through double slit then you get this pattern. See, white central maximum, that is this one, surrounded by areas of darkness, those are called dark fringes, because there you have destructive interference. For example, when the crest of one wave meets the trough of another wave, and if they have the same amplitude and all, if they are coherent, then there is destructive interference. The amplitude there becomes 0. That's why it's a dark fringe or dark area. And further bright spots that have decreasing brightness from the center. So you can see that here. And also diffraction grating. That's another topic. And this is the pattern that you get from the diffraction grating. This is done with monochromatic light laser, but this is done with visible light. I think that's why you get the spectrum of white light you can say. Okay, so let's go back to what we were discussing. Alright, so here we are. Then, or reflecting waves from a grating, as we saw in figure H, that is the diffraction grating of section 5.2.3. Now here we have the Davison and Germer reflected a beam of electrons from a nickel crystal. So you can have a look at this diagram. This is the nickel crystal filament. Now remember, you would have learnt about thermionic emission in the O-level class, where there was a filament that was hot, and because it is at a high temperature, it gave out electrons, and you had the anode here. Anode is negatively charged there, and this was the cathode. Cathode is giving out the electrons, and since there is a positive charge here and this is negatively charged, the electron is repelled from here and attracted here. Thermionic emission, because of the high temperature, the metal or filament gives out electrons. That is called thermionic emission. Then because of this positive charge, the electron is accelerated towards it. So that's why this is called the accelerating anode, and it is the electrons are allowed to pass through this gap, which will create an electron beam. Electron beam goes like this, and they are reflected a beam of electrons from a nickel crystal and measured the intensity of the reflection at different angles. So this is one particular angle that is shown, so you can move this like this and detect the intensity of the reflected electrons at different angles. In 1927, Davison and Germer tried to detect diffraction of electron waves when they reflected from a crystal of nickel. Figure B illustrates the experimental setup. They measured the intensity of the beam at different angles for various accelerating voltages. Okay, so you can see intensity of the beam at different angles for various accelerating voltages. Now, if the voltage, that is the potential difference across these two, is high, the electron will be having a greater speed once it leaves this anode. That means there will be a greater acceleration here when it is accelerated, so it will have a greater speed. So they changed the voltage to get various accelerations and plotted a graph of their results. Figure C shows the graph for a beam accelerated through 54 volts, and you can see that here. So when the voltage here is 54, this is the graph you get, and you can see the intensity is maximum somewhere here when the angle is 50 degrees. Davison and Germer's electron beam reflection from a surface of atoms acting as a reflection grating. Okay, so electron beam reflection from a surface of atoms. Now remember, this is a nickel crystal, so if it's a crystal or if it's anything, there are atoms in this, and the electron is sent like this, so it gets reflected by the reflection from the surface of atoms on that crystal. See, from a electron beam reflection from a surface of atoms acting as a reflection grating. Remember earlier when you learnt about waves, you learnt about the diffraction grating. So there is a comparison here. That's why we went back to chapter 5.2.3 to see the diffraction grating. Here we have reflection grating, which is this. The atoms of this is the reflection grating. Again, electron beam reflection from a surface of atoms acting as a reflection grating showed variable intensity at different angles, exactly as is observed with waves. So you can see a similar pattern. Now remember, in the case of waves also, the brightness of those fringes decreased from the center. We saw it when we saw the diagram for the diffraction grating, where we saw the central fringe had the highest intensity. So here also you can see the intensity is generally decreasing. So we can see variable intensity at different angles, exactly as is observed with waves. Not only did Davison and Germer prove experimentally that electrons can behave as waves, but their results also show calculations of the distance between atoms in the nickel crystal. This has given rise to advances in the study of atomic structures using electron beam crystallography. Okay, so this has given rise to advances in the study of atomic using electron beam crystallography. Okay, so let's go to the next one, de Broglie equation. So you should know this. In 1924, a French prince called Louis de Broglie suggested electrons could behave as waves and proposed an equation to calculate their wavelength. This is very important. Their wavelength is inversely proportional to the momentum, because h, that is a constant. Their wavelength is inversely proportional to the momentum they have when considered as particles. Okay, so this is the equation in words, and here we have the equation in symbols. Electron wavelength lambda, these are all in SI units, meter, joule, second, like this. And you saw how we got this unit. Remember, in E equals HF, H was equal to E over F, and that's how you can get this unit. E is the energy, that is in joules. F is the frequency, so that is in hertz or per second. When it comes up, you get joule seconds. Then momentum is mass times velocity, so the units of mass is kilogram, velocity is in meters per second. Now let's go through an example using this equation. So very important equation. You may have calculations with this. Calculate the wavelength of electrons traveling at 10% of the speed of light. 10% of the speed of light, you know the speed of light is 3 into 10 to the power of 8. So 10% means 10 over 100, which is 0.1, or 1/10 of the this speed. So that's why we multiply by this. And the mass of electron, it is given to you in the data sheet. You can see it is this much in kilograms. H is the Planck's constant, that is also given in the data sheet, 6.63 into 10 to the power minus 34 joule seconds. And then you will get the de Broglie wavelength of these electrons traveling at this speed, 10% the speed of light. So you can see that is the wavelength of those electrons, because electrons can behave as a wave in addition to behaving as a particle. Investigating electron diffraction. So this is important. An electron diffraction tube demonstrates the wave nature of electrons. Investigating electron diffraction, although they are quite expensive, some school laboratories have an electron beam diffraction tube. So you can see here, electron beam diffraction tube demonstrates the wave nature of electrons. So that is the purpose of this instrument. It demonstrates the wave nature of electrons. Electron beam diffraction tube demonstrates the wave nature of electrons. This accelerates a beam of electrons through a high voltage. Now previously we saw here also, because this is positive and this filament is negative, the electron is repelled from here and attracted by this and as a result the electron is accelerated. Similarly, over here also this accelerates a beam of electrons through a high voltage and then passes the beam through a sliver of graphite. Okay. The array of carbon atoms in the graphite acts as a diffraction grating in 2 dimensions. Now, graphite is an allotrope of carbon. When you learned, you would have learned it for chemistry. There are about 3 allotropes of carbon, graphite, diamond, and another one, and that means it's made up of carbon atom. So when you send this beam and through this and then passes the beam through a sliver of graphite, the array of carbon atoms in the graphite acts as a diffraction grating in 2 dimensions. Remember, diffraction grating we have seen when we learned about waves. I showed it today also, which produces a circular diffraction pattern. So here this is what you can see. You can see, if you look closely, you can see circles here. That is the circular diffraction pattern. The front end of the tube has a phosphorescent screen that will show up the diffraction pattern. So when the electron strikes the surface, it will produce a light. So that's what this means. If we make careful measurements of the dimensions of the tube and the diffraction pattern produced with different accelerating voltages, we can carry out an approximate calculation of the atom spacing in graphite. Now remember, atom spacing in graphite here because we use this sliver of graphite, and previously we had this nickel crystal. So using this we could calculate the distance between atoms in the nickel crystal. Similarly, here also atom spacing in graphite, we can find the spacing using this method. So now you know the use of electron beam diffraction tube. It can be used to demonstrate the wave nature of electrons, and in addition to that you can find the atom spacing in the material, which is in this case graphite, that was used as a diffraction grating in 2 dimensions to produce this diffraction pattern for the electrons. Okay, then we have 2-slit electron interference. Okay, so we saw one example using this, and then here we had reflection, but over here we have diffraction. Now we saw electron reflection, but even with reflection we could find the atom spacing, and here we have diffraction, investigating electron diffraction. Here we have the electron beam diffraction tube, which can be used to find the atom spacing in graphite. And now we will see 2-slit electron interference. In 1965, Richard Feynman suggested that electrons should also be able to produce the 2-slit interference pattern seen with light, as they can behave as waves. Recently, this has been shown to be the case, giving further evidence for the wave nature of electrons. So, if you remember the Young's double slit experiment, it is also called the 2-slit interference pattern experiment, 2-slit interference pattern. And since electron shows wave properties, that means we can verify it further by doing this 2-slit interference pattern with these electrons. So this is what he suggested, that electrons should also be able to produce the 2-slit interference pattern seen with light. That is what we saw under the waves chapter, as they can behave as waves. So that means as the electrons can behave as waves. And here you can see recently this has been shown to be the case, giving further evidence for the wave nature of electrons. So let's have a look here. Recent experiments have been able to demonstrate electrons producing an interference pattern when passed through a 2-slit type experiment. These 5 images here show the same image after different amounts of time. The particle electrons hit the screen in places that slowly build up the wave interference pattern. Now you can see here, these are like the bright and dark fringes that you had in the double slit experiment or two slit experiment in the case of waves. We saw it today. I showed you that in chapter 5.2.3, I think. Okay, so here you can see with time A, B, C, D, E, you get this. So you can see the particles electrons hit the screen in places that slowly build up the wave interference pattern. However, the latest research has allowed scientists to observe that the interference pattern is built up by the movement through the apparatus of the individual electrons. So you can see again, interference pattern is built up by the movement through the apparatus of the individual electrons. They are behaving as both individual particles and waves at the same time. They are showing wave-particle duality. Okay, now we will see the electron microscope, how it applies to this. One of the most important applications of the wave nature of electrons is its use to study objects at very small scales. An electron beam can work like a beam of light, but with some different properties that can make the electron beam much more useful for microscopy. So an electron beam can work like a beam of light, but with some different properties that can make the electron beam much more useful for microscopy. The main advantage is that the wavelength of an electron beam can be controlled by altering the voltage. So you can see again, you can vary the wavelength of an electron beam by altering the voltage applied to the accelerate the electrons. Now remember earlier we saw how the electron was accelerated. So if you can change the voltage here, potential difference here, then you can change the wavelength. In some instances, this can mean the wavelength of electrons in the beam can be 10 to the power minus 10 meters, the same size as atoms. Okay, so you can adjust it so that you get this wavelength for those electrons. So here it's mentioned wavelength of an electron beam can be controlled. Electron beam. As a rough rule of thumb, the minimum sized object that can be imaged by any wave is about the same size as the wavelength. In this example, the electron waves are 1,000 times shorter than light waves, and so they can produce images of objects 1,000 times smaller than visible light. Okay, so I think this is clear. So there are 2 points here. The minimum sized object that can be imaged by any wave is about the same size as the wavelength. And the second point is the electron waves are 1,000 times shorter than light waves. That means they can be used to produce images of objects 1,000 times smaller than visible light. For example, here, remember the range of the wavelength of visible light? You would have learnt it. 400 to 700 nanometers is the wavelength of visible light. Electron microscope can have a magnification of up to 10 million times. You have the light microscope and the electron microscope. Now we are talking about the electron microscope. So you can see electron microscope can have a magnification up to 10 million times. These bacteria are about 1 micrometer long. Okay, so if you multiply this by 10 million, you can see how big it is that you are seeing through the electron microscope. Electron microscopes can have sufficient magnification to see the results of manipulation of individual atoms. This atom boy image was made by researchers at IBM who moved the individual carbon monoxide molecules on a surface of copper metal. So okay, so you can see individual atom manipulation of individual atoms. See, atom boy was made by researchers at IBM who moved individual carbon monoxide molecules on a surface of copper metal. Alright, so we have arrived at the end of this chapter. There are questions here, you can do them, and in the next chapter, the next subchapter or next part, the definitions are here, but this applies to this only. So basically here you don't really have any definitions to study, but you should know this. Now what we saw here again, now I think you understand this. Explain how diffraction experiments provide evidence for the wave nature of electrons. So first we saw this, and then we saw this experiment, okay, and then after that, to verify further, we saw this one, that is the two-slit electron interference. So that all three explain how diffraction experiment provide evidence for the wave nature of electrons. Describe other evidence for wave nature of electron, that is this one. Here we have diffraction and interference. So three were there. And remember, here it acted like a diffraction grating. Actually not there, over here, okay, this acted like a diffraction grating. It's mentioned somewhere here, see. So you get this, and here it was sent through double slit, and then you get the interference pattern, like in the case of Young's double slit experiment for waves. Then we went through the de Broglie equation, lambda equals h over p. So very simple, just 2 pages are about this topic on electron diffraction and interference. So here you have reflection, here you have diffraction, and here you have interference. So 3 things: reflection, diffraction, and interference. And also we learned about electron microscopy, because we can control the wavelength of the electron beam by varying the accelerating voltage. So you can see in some instances this can mean the wavelength of electrons in the beam can be this much, which is the same size as atoms. And we learned this, that the minimum sized object that can be imaged by any wave is about the same size as the wavelength. So if we can get this wavelength, that means we can get an image for that sized object. And over here we saw in this example the electron waves are 1000 times shorter than light waves, and so we can use this in the electron microscope to produce images of objects which are 1000 times smaller than visible light, because electron wavelength can be 1000 times less than visible light. So that means we can produce images of objects 1000 times smaller than visible light. For example, like this electron microscope can have a magnification up to 10 million times. These bacteria are about 1 micrometer long. 400 to 700 nanometers is the wavelength of visible light, but this is 1 micrometer, which is bigger, right? 400, yeah, 7, yeah. And then we saw this electron microscope have sufficient magnification to see the result of manipulation of individual atoms, like here. Okay, you can see individual carbon monoxide molecules on a surface of copper metal were moved, and you get this. They make this image. Okay, so make sure you answer all these questions and check the answers in the answer sheet. That will ensure that you understood this content better. Next we will see atomic electron energies, where we have the energy levels. So let's do that now.